Thank you guys all for coming and welcome to the dynamics morning, I guess, of the conference. It's my great pleasure to introduce our first speaker, Alex Eskin. Alex got a PhD at 93 from Princeton, extremely decorated mathematician. I couldn't fit all this in the notes I have. His work starts from number theory to homogeneous dynamics to Teichmuller theory, I want to say, since that's my field. He has won numerous awards, including a Clay Prize, Breakthrough Prize, and ICM talks at 98 and 2010. Please welcome Alex Eskin.
Thanks for the embarrassing introduction. So today I'm going to talk about this is a joint work with Aaron Brown, Simeon Philippe, and Federico Rodriguez-Hortz. Okay, sure. I'm sorry. So anyway, everything which I'm going to say, which is somewhat new, is joined with these people. A lot of the stuff will be reviewed. So let me start with some sort of review. So the first topic I want to talk about is really, well, first, what is the problem? I mean, what is ergodic theory? So you start with a map from some space to itself. Let's say X is some compact, nice compact space. And well, what I really want to do is I want to look at the orbits of a point. So pick X, X, and then I want to understand the orbit of X. So I look at, and the typical question. So actually, this is dynamical systems. And if you want to do ergodic theory, then you also assume that T preserves a measure mu. And always mu of the whole space is equal to 1. And so if you pick a point, you want to understand the orbit of this point in some sort of statistical way. And typically what you want is this equidistribution theorem. So you want, so I want average with respect to, I guess. So you want this to converge to something. And well, the most natural thing for this to do is to converge with respect to the invariant, to integral of f with respect to the invariant measure. Yeah, sorry. Thank you. Okay, thank you. And so this is actually a theorem, which is a classical Birkhoff ergodic theorem in 1930s. So this is true for almost every X, provided mu is ergodic. And what does ergodic mean? It means that any invariant set as measure 0 or 1. So this is a classical theorem in which like a huge swath of mathematics have been built. And it's very wonderful. It's amazingly general. It does, like every theorem has a weakness. And the weakness of this theorem is this almost every. So you don't really know what happens if somebody comes to you and says, I don't care about almost every point. I have this one point I care about, tell me what happens at that point. Then you have to very politely tell them to go away. So you can try to improve this. I mean, for like lots of applications, you really do want to know what happens in individual points. And there is a situation which was, so now we are going to jump from 1930s to 1990s. So this is a theorem due to Ratner. Well, actually, maybe I'll state the setup first, and also a lot of the stuff is actually also done by Margulis. And so here is the setup. So G is a Lie group. and gamma is a lattice in G. So here I should think of G as being like SLNR. Should think of gamma as being SLNZ. And U is one parameter unipotent subgroup of G. So unipotent just means all eigenvalues are always equal to 1. And so an example would be something of this form. So this is these matrices are a subgroup of SL3R, which is unipotent. This is actually the example which was most famous because it was led to the proof of the Oppenheim conjecture. And so what is a theorem? So then there's kind of 3 statements which are basically all trying to say. So the point here is that in this system, you can understand the orbit of every single point. So I guess maybe first, what is the system? U acts on G mod gamma by left multiplication. So this is a dynamical system which is nice. It's very nice. I mean, in particular, it's homogeneous. G mod gamma, every point looks like every other point. So it's called homogeneous dynamics. And the fact that it's unipotent is crucial for the proof. If you drop this assumption, as stated, the theorem is false. But so the point is you can understand the orbit of every single point. So maybe I'll write down what are the 3 statements. One is, well, I guess for all x, the closure is, so if I look at the closure of any orbit, is a closed orbit of a subgroup L, which is sitting between U and G. So in particular, it's a manifold. So it's a very special kind of manifold. So the orbit closures are manifolds. If you drop the assumption that this is unipotent, then orbit closures are typically some sort of complicated Cantor sets or warps. So this is they're very, very complicated, but this is quite a remarkable statement. And again, now if it wasn't true for all x, if you just wanted almost all x, just followed immediately from Berkowitz theorem. But the fact that you understand every x is what the point here. The second statement is that all ergodic invariant measures are essentially supported, push forwards of the Haar measure on some sort of, again, intermediate subgroup. So here the closed orbit of subgroup L supports an L invariant measure, and this is saying that all the ergodic invariant measures are of this form. And the third statement, and I'm not going to write it at all, but basically any orbit is uniformly distributed in its closure. So of course, so closure depends on the point, but if once you know the closure, then you understand the orbit splits out evenly. So this was proved that this more than 30 years ago. It's amazing. I mean, there's an awful lot of applications of this, like the number theory to other things, to geometry. People are still finding new ways to use it, which is kind of, I think, kind of amazing. So this kind of theorems are kind of the crown jewels from my point of view. So we're trying to figure out if we can, and also, in what extent can you generalize this? So there is one direction which I'm not going to go into at all, but it's well, first you can just say, well, what if I drop the unipotent assumption? For example, if I start looking at some diagonalized something like e to the minus, like this kind of group, then you can be easy to see that everything goes wrong. Orbits are fractal and so on. This is typical behavior in dynamics in some sense, which you expect, but you don't have this. So, okay, then fine, you don't do this, but then turns out that if you actually work not with one element, but with several different elements which commute, again, in this homogeneous setting, then maybe you can say something. And this is, there was actually Fields medal going for progress on this, the London-Interschauss on this. But this is a very well-known problem, and then somehow I think it's much more difficult than anything I'm going to say about right now, so I'm going to stay away from it. Now, you can also try to, I mean, the main problem with the proof is that the proof, basically what do? You have your unipolar matrix and you conjugate, so you have this unipolar matrix, this is like this, this unipolar matrix, and then you conjugate it by some. So this is U and this is U inverse, and maybe depending on the parameter T. And you kind of look at the result, and you look at the matrix centers of the result, and you really want them to be polynomial in T. This is absolutely necessary for the proof. And if they're not just have polynomial upper bounds, it's not good enough. Or if it's just anything other than polynomial, then it doesn't work. So the proof is very, very special to the situation. And so it's very hard to chat. I mean, really, people didn't really know how to generalize this kind of theorems, or if they, even if there are kind of theorems in other settings. And now there is another theorem which is actually quite big. There's a Benoit-Kahn theorem, which is going to be kind of has to do with sort of random dynamics, which is going to be something which but again, in the homogeneous setting, I'll come back to this later. And then also at some point, Mirzakhani and I actually found some analog of this theorem working on the moduli space of Riemann surfaces. I'm not really going to talk about this at all. This is technical dynamics. The proof is very, very different from this one. And it is that proof which is basically what I'm going to talk, is what leads to what's happening today. So today I'm going to try to work in a completely different setting. And by the way, if you told me 10 years ago that you should try to prove some analog of Ratner's theorem in this setting, I would have just laughed out loud. I mean, it makes absolutely no sense. It's way too general. Because see, all of those theorems kind of seem to require an awful lot of structure. So there have to be a lot of stuff going on in order to prove something like this, because this is, I mean, very far from expected behavior. But so what is the theorem that I'm going to talk about? So I'm going to take M is going to be some sort of compact manifold, and I'm going to pick some mu is maybe finitely supported measure on the diffeomorphisms. So I'm going to see infinite diffeomorphisms. So really, what this is kind of fancy way of showing. Basically, the example you should think of is I pick two diffeomorphisms, F1 and F2. If I pick two different, and then mu is going to be 1/2 times delta at F1 plus 1/2 times delta of F2. So what I'm really going to do is I'm going to do the following. I'm just going to apply. I'm going to take a point X, and I'm going to apply F1 and F2, which is probability 1/2, and I'm going to get some sort of dynamic, I mean, kind of a random dynamical system. But I can also think about just the group. I can also think about the orbit. So I can think about just, what is the closure? So I look at the group generated by F1 and F2, and then I act on X, and then I can, for example, ask what can I say about these kind of things. And again, the answer shouldn't probably nothing, because I haven't assumed anything. But it turns out that it somehow seems like sometimes you can almost get something from nothing. So before I start trying to talk about any sort of theorems, there is kind of an example in which actually, okay, maybe before I get to the example, let me talk about, I want to introduce one other thing. So I wanted to introduce what's called a stationary measure. So if I want to approach this question using ergodic theory, as opposed to just topological dynamics, I want to have a measure. So the problem is there might not be an invariant measure for both diffeomorphisms. If they generate non-amenable group, there is no reason to believe they have an invariant measure. And so you define a measure, and let's say nu on M, it's called stationary. Okay, sorry. If so, what I want is if I want to think about integral. Well, this is gonna look ridiculous. Sorry, I want to just. And this is really just, I should think this is really just pushing the forward. So I push a measure nu by f1, it might be different. Then I push the measure by f2, might again be different, but if I take the average, then you should get nu back. So this is what's called a stationary measure. It's not invariant, but it's invariant on average. And stationary measures are somehow the right object in this game. If they're certainly the right object if you want to talk about orbit closures, because turns out the closure of any orbit supports a stationary measure. It's very easy to prove. It does not, certainly there is no reason to believe they're in invariant measure. But okay, so this I just define a stationary measure. So now let me look at the example. This is an example which I think is very familiar to most mathematicians. It's just I look at, maybe I just pick F1 and F2 in SL2R, two matrices. Maybe I'll call them A1 and A2. And act on the projective space by Mobius transformations. Mobius. So I have this familiar picture. You have the circle of infinity. F1, they're both kind of, I mean, I'm assuming both of them are hyperbolic. So they're kind of, so F1 has a contracting fixed point and an expanding fixed point. So essentially, the only, if you look at measures just invariant by A1, it's going to be only here or here because everything else goes to one of those points. And, but then it's not going to be invariant by A2. So there is no invariant measure. And there are always stationary measures, so there's lots of stationary measures which are not invariant. I'll just maybe. So this is, okay, so maybe I'll just, another bullet point. Now, orbit closures are complicated. So it's actually any limit set of a Fuchsian group is going to be an orbit closure. I mean, you can easily imagine just take two matrices that will active by a point to get some sort of complicated fractal in general. And the last item is something which, I mean, I use a term which is very familiar to all dynamicists, but I think I'm going to have to define it. It says all Lyapunov exponents are negative. So what's a Lyapunov exponent? Well, if I have this kind of random dynamical system, so I'm going to think about a future which is going to be I'll write it like this. So each omega I is either F1 or F2. And then I'll write maybe capital F sub n. This is going to be omega 0 to, well, I'll write those out. I guess I'll want another order. So I just multiply them together. And now, if I look at lambda, so I'm going to define Lyapunov exponents in the minimal way, even though it's not the right definition, but just I want to say a little about this as possible. And, well, these are the eigenvalues of the derivative of. I'm thinking of just of these as being diffeomorphisms. So this is a diffeomorphism has a derivative. So this is a matrix as eigenvalues, and then the lambda. And I'm also gonna, I guess, order them in decreasing order. And the lambda I, this is I's Lyapunov exponent, is the limit is n goes to infinity of 1 over n times log. It's this. So it's basically the asymptotic growth rate of the nth exponent of this problem. Now, this is not the right definition, but it will do for my purposes. So maybe a few observations. Lambda 1 bigger than 0 means there is some exponential growth. Since this is what the public thinks of as a butterfly effect. Right? To make little change in initial conditions, things kind of change exponentially fast. So this is precise definition of what that is. And all Lyapunov exponents are negative, just means that everything kind of contracts, which is exactly the picture here. On the projective space, everything kind of seems to contract. So this is bad from my point of view. And now, let me maybe write this one theorem, which is, I guess, this is the theorem that's joined with these people. So suppose maybe I'll write like this. Either sorry. Suppose okay, well, actually, maybe let me define. Actually, let me make a definition before. I think I'm sorry. I'm going to define make another definition. A negative subbundle is an invariant subbundle of the tangent space. So invariant means invariant by both F1 and F2, on which the sum of the Lyapunov exponents is negative. So the sum just means kind of the volume of that subbundle contracts. And so now the theorem is that suppose there exists no negative subbundles. then any stationary measure is invariant. So you cannot have like non-invariant stationary measures unless somehow to me putting in a negative subbundle is kind of like secretly putting in some copy of projective space inside your system. If you don't do that, then you really don't have this kind of behavior. Also, in this case, I think I won't be able to say exactly what. Maybe I'll just write down the. I'll just write it. So conditionals. I'll write the statement without really explanations because I don't have time to explain it. Of any invariant measure are homogeneous. So I'll just write it like this. This is some sort of progress towards measure classification problem. It kind of gives you a lot of control over the measure. So there is a lot of information which is buried in here, but I don't have time to unpack it because it's a very short talk. Now, I guess this is actually a 250-page proof. So I'm not going to be able to say much about the proof either, but I want to highlight some feature of it at some point. So kind of the moral of this is that either you have this negative subbundles or you're somehow in a Ratner world. You expect to have some sort of measure rigidity like in this homogeneous space situation. So if you push the system far enough, you can work on it. I mean, the theory is not complete, but at least the expectation is that you really do get like Ratner-like phenomena in a very, very general setting, as long as you don't have this condition. I'll also try to figure out how do you ever check that there is no invariant negative subbundles. I'll put some condition which implies this, and why it's a reasonable condition. If you prove the complete, I mean, there are situations. I mean, if you can show everything, I mean, we don't quite have a complete theorem here because we don't quite have complete measure classification in this generality. We have some sort of, if you do get a complete measure classification and you do more work, then you get it arbitrarily distributed. But that's what you expect. Yeah, and there are some situations, I guess, I mean, I won't talk about this, but there are some situations where we can actually expect to be able to carry out this program completely, for example, actions on character varieties. So in there you should get to that. Okay, so maybe how do you rule out negative subbundles? So there is another condition, which is what you call uniform expansion. Sorry. So so suppose so what is this? This is the condition. So there exists N and C such that if I look at integral, I always feel silly writing this kind of stuff. For all x in my manifold, all tangent vectors. If I look at, sorry, I have to give myself a little bit more room. ran out of room. So this is supposed to be bigger than C. So what is this really? Maybe it's I'll just write it again because it's like the average. So it's really 1 over 2 to the n. This is average over wards in F1, F2 of length n. And then here, let's call the word f, and then I again have this in log. I look at df. And c is bigger than 0. So this is saying that on average, if I apply like a random word to a vector, it gets longer. And so if I average over all the words, I really get, on average, I get things longer. And this is supposed to be uniformly over the whole manifold and over all the vectors. So this is like a universal condition. So now, why is this reasonable? First, why should they get longer and not shorter? And this will also relate to why things go very wrong for why. I mean, I'll make another comment. So suppose you just have a single map. So if you have a single map, then you expect the action on the tangent space to be given by some sort of hyperbolic matrix. So it has a positive, so it has an expanding, it has like an expanding direction, and you have a contracting direction, right? So this is what you expect for a typical word for any given f, right? And so of course here things don't quite work the way you want, because if you pick a vector here, then okay, it's expanded, but the vector here gets contracted, which is no good, right? So it looks like there's complete symmetry, but of course it's not symmetric, because if you take like a vector at 45-degree angle, it also gets expanded. So it's not really, in order to be contracted, you really have to be, because it's expanding component is expanding, and so in order to be contracted, you have to be very, very close, essentially on the contracting direction, right? So it's possible to, for a single map, it's possible to have this. If you have like an abelian commuting system of maps, then of course all of them compute, they'll all have the same picture, and again, things will not work because anything in the contracting direction will be contracted. But now imagine you have a non-abelian group acting. So you have lots of different words, and each word will have its own picture, right? It will have its own expanding and its own contracting direction, right? And you somehow, so the contracting directions don't coincide. So if somebody is contracted by the first word, it's expanded by the second word, and you expect the average to be positive. So it's very, very difficult kind of to imagine this not working. You kind of have to have a conspiracy against you. So somehow, to me, this condition could be quite difficult to prove, but it's actually a finitary condition. So this is a capital N. This is also capital N. So I have words of fixed length. It's a finitary condition, so you can check it on the computer. And actually, I've had a student actually try to do that at some point. It's surprisingly difficult, but it's possible. So somehow, when you're given any sort of kind of random dynamical system like this, you can ask if it has it, and I would say, yeah, it should probably has it, unless you can give me a reason why it shouldn't. And there could be reasons why it shouldn't, but you really expect it to be true. And then it's easy exercise, uniform expansion. Implies no negative subbundles. Unfortunately, this thing only implies no of dimension 1. No one-dimensional bundle cannot be contracted. But in order to rule out uniform, you need to generalize this definition. So I can, instead of working on the tangent space, I have to work on some sort of Grassmannian. But there is none of this condition which works like this, and then this will. So you can talk about uniform expansion in dimension D. and the uniform expansion in dimension D implies non-negative subbundle dimension D. So this is a kind of tells you that this, in some sense, this behavior looks like it's very common. And this does give you a Ratner-like theorem. If you actually assume uniform expansion in all dimensions, then you can prove that any invariant measure is either absolutely continuous vector volume, which basically is volume, or it's finely supported. So you kind of have a kind of almost a complete classification, and then you can also do other things. So maybe one, yeah, kind of almost out of time. I just want to make one more comment about how the proof goes. So the proof, well, it's horribly long. It takes. I'm not going to give you the outline of it, but there is just one mystery, which was, for example, Miriam and I were working on this in technodynamic sense, and somehow all of the theorems are in the end are about proving that some measure is the Lebesgue measure. You have to show something is invariant. So invariant means the condition measure along the orbit is the Lebesgue. So how do you prove a measure is the Lebesgue measure? Well, we all learn how, in undergraduate, or maybe depending on, is that measure is the Lebesgue if it's invariant by arbitrary small translations, right? Now, if you're an ergodic theorist, you know that another way to prove measure is the Lebesgue is by showing it has maximal entropy. This works for some things, but not for everything. And in most of the arguments, you actually have to combine both methods. You have to use both. But in this setting, we have a manifold, arbitrary manifold. So what does invariant by translations actually mean? This makes absolutely no sense, right? So this is why in techno space it does. There is an affine structure on the moduli space, and invariant by translation makes sense. And when you're working on the techno space version, we're absolutely sure it has no generalization anywhere. But it turns out to have part of some much bigger story. And the story is the reason that it's part of this bigger story is a theory of what's called non-stationary normal forms. I'm going to be out of space here. And maybe the people involved there are many people involved in developing this theory. Katok and Spatz here. It was actually in its final form. It's by Kalinin and Sadovskaya. And what does it tell you? It tells you the following. So this is actually an amazingly general thing. So I'll probably try to finish it here. Is it suppose you have a diffeomorphism? This is maybe is this really you can apply to the random setting, but it's something about a single map. So if you have a diffeomorphism, by the way, most of our theorems are really about a single diffeomorphism. So the random dynamics kind of built on top of this. So if you have, so it has a foliation by, let's say, unstable manifold or stable manifold. Stable manifold just means things which come together as you go forward. Unstable manifold things come together as you go into the past. I'll talk about unstables for some reason. So the unstable manifolds are kind of, squiggly curves. The foliation is not, these are smooth manifolds. If F is smooth, but the foliation is not smooth as a whole. But it's still, they have no kind of special structure. They're just kind of smooth submanifolds of your original manifold. But it turns out there is sort of a change of variable, which is called the normal form, which converts these to, well, what I'm drawing. These are homogeneous spaces for a certain nilpotent group, for some called GSSR, which is a nilpotent Lie group associated to F. And it depends, what the group is depends on the Lyapunov exponents. And so you kind of have a picture here. So you have on this side, you have the dynamics. So I'll try to. So here I have my squishy, my squiggly manifold, stable manifold. I have F, which translates into another one. And here on the other side, I have these kind of homogeneous spaces. So I have this map, which is the normal form map. And I can do it here and here. And these are homogeneous spaces for this nilpotent Lie group. And here you act by some sort of by solvable Lie group. This isn't something in this map is an element of what's called the subresonant maps, which is really basically the automorphism group. So it's a solvable Lie group. So you have kind of conjugated your dynamics to something which looks like kind of like a homogeneous. And here you can talk about being invariant. Like this is a homogeneous space for a nilpotent Lie group. You can ask about being invariant by some sort of one parameter subgroups of this group and so on. So all the structure is here. Now there are lots of problems because the issue with this change of variable is that it's smooth along the unstable manifolds, but it's only measurable transversally. So it's not like a global picture, but it's still good enough after a lot of work to carry out this kind of thing. And so anyway, that's all I wanted to say. I can write down the formula for it. I think I'm kind of out of time, but I'll write down the formula. It depends only on the Lyapunov exponent. So it gives you a collection of numbers. I can write a Lie group associated to that. It's a group of subresonant maps. I don't know anything other than that. Strictly subresonant maps. Yeah, it's quite amazing that it exists, and it hasn't been used that much. I mean, it has been used in some other. I mean, the theory is only measurable, which is maybe why people don't. People that are done, but it's actually is very useful.